Welcome to Chemistry Class 12. Today I am beginning with a very important concept, that is Van Hoff factor, which is symbolizes as small I. But see, it is written here abnormal molecular masses. So let's see, what does it mean? What is abnormal molecular masses? I have explained these terms in my earlier video. What are these? Non-volatile, non-electrolytic solute and electrolytic solute. And these terms, dissociation and association, I have already explained, but let's have a brief revision here and see. It's written in non-volatile, means what? Which does not readily changes into vapor. This is of non-electrolytic type solute, means what? Which do not ionize in solution. Examples are sugar, urea and sucrose. You have seen these molecules in determination of colligative properties earlier. I have written it here and I will explain it later. You have already done all these molecules earlier. Now let's see what is electrolytic solute. Electrolytic solute is that which undergoes dissociation, and these are of two types. What happens with the electrolytic solutes? They are dissociating chemically and changing into their ions. The capacity with which they do so is being categorized strong electrolyte and weak electrolyte. Example is already written here. See, NaCl, KCl in water, they are strong electrolytes. And weak electrolytes are, one example is written here. It means that it does not dissociate completely. I am focusing here on strong electrolyte. Let's see. Just pay attention on this equation. It's written here, NaCl solid. When it is dissolved in water, its molecules ionizes and they give rise the ion, sodium ion and the chloride ion. Since it is a strong electrolyte, so we consider 100% dissociation here. In that case, if I have taken 1 mole of NaCl, after dissociation it changes into 2 ions, and each of these ions are having 1 mole. That is 1 mole each. So what does it mean? After dissolution in water, 1 mole is changed into 2 moles. Now, since we are doing here colligative properties, and you can see here, these are the formula, we have derived it earlier, and you have seen that these depends on number of moles. That is, the colligative properties are those which depend on number of particle and which does not depend on their nature. So what does it mean? That on dissolution, if we are considering one electrolytic solute, on dissolution the number of particle increases here. You can see here. Okay. Now let's see the another concept here, that is a association. There are some molecules which combine together to form aggregates. Now let's see these terms also. When 2 molecules combine, it is forming dimer. When 3 molecules, it is called as trimer. 4 molecules combine together and form aggregate, we call it tetramer, and so on. Number of molecules are aggregating with each other and we call it polymer. Now let's see one example here. I have taken this example of acetic acid. Now see, 2 moles of acetic acid. When these 2 moles of acetic acid are under solvation, they are forming a dimer. They are 2 molecules. The structure is being shown here. See what happens here. This is the hydrogen bonding. This dotted line you can see here and there. This is one molecule and this is the another. And they are forming their dimers. Exactly the same way benzoic acid, this also forms a dimer. Because the formula is same, it means the functional group is same in the benzoic acid also. And what is it here? It is going to be C6H5 and COOH. Exactly the same way C6H5 and COOH, and they are also that benzoic acid also forms a dimer. Here this is an example of acetic acid. Now what does it mean actually? How we are concerned with this dimerization in this chapter with the Van 't Hoff factor? See what happens here. The solute particles present in the solution are less than expected. Because what does it mean? You have taken 2 mole. Under solvation, it becomes 1. It's a huge molecule, but it is considered as only 1. So what does it mean? There is the decrease in number of particles. And what has happened in the dissociation? There is increase in the number of particles. And what you are learning, you are studying the determination of the molecular masses on the basis of number of particles, and this is the colligative property. Now let's have a quick recap here. This is what? Lowering in the vapor pressure equals what? This is number of moles of the solute. This is mole fraction of the solute, which in turn equals a number of moles of solute upon total number of moles in the solution. And what is this N? N is equal to W by M. You know that. Now this is what? Elevation in boiling point, which is equal to ebullioscopic constant, and molality. What is this molality? I have opened up and written here number of moles of solute upon mass of solvent in kg. So how we are concerned here? We are concerned in this molality, we are concerned with the number of the moles. That is what? The number of particles. See, this is what? Depression in freezing point, the cryoscopic constant, molality. It is the same. That's why I have written here dotted line. The same you can write here. Now let's see. This is the osmotic pressure is equal to CRT. What is C? Molarity. Molarity N by V. Again, what is this? Number of moles. So this, therefore, this is the colligative property. All these 4 colligative properties, they are dependent on number of moles. Now, what is the inference drawn here? See, what does it mean? The observed colligative property differs with the normal colligative property. What is the observed one? This is the observed one. In case of dissociation, if the solute is electrolytic, it will undergo dissociation, and so normal colligative property is different, but observed colligative property is different here. It is more in case of dissociation, and here also see the observed colligative property, that is the number of the particle, differs with the normal colligative property also. In this case, that is in case of association. So just to solve this riddle, Van 't Hoff in 1886 extensively studied the phenomena of molecular association and dissociation of a solute in solution and its effect on colligative properties, and introduced a factor which is known as Van 't Hoff factor and symbolized as I, to express the extent of association and dissociation. It is defined as, let's see, Van 't Hoff factor defined as the ratio of the observed, that is experimental, value of a colligative property to the normal, that is calculated value of the same property, is termed as Van 't Hoff factor I. Now let's see, mathematically it can be written as I is equal to total number of moles of solute after dissociation or association upon total number of moles of solute before dissociation or association. Now I would like to resolve it again, make it more clear. Now let's see, what is this total number of moles of solute after dissociation? It is more, okay, and after association it is less in case of this particular type of the solute. And total number of moles of solute before dissociation, we have taken 1, and total number of moles of solute before association, again we have taken different here, right? So that's why this I is equal to, and again see this, I have written here delta OBS observed and delta calculated. What is this? These are representing the observed and calculated value of the colligative property. So there is something more left. This is the degree of dissociation and degree of association. We are going to learn it in the next video.